Hi, my name is Justine Harkness, and in this video, we'll look at how to calculate the change in energy as we move charges through electric fields. Work can be defined as a transfer of energy by a force applied over a certain distance. And if we look at the equation for work, it's force times the displacement times the cosine of the angle. And let's think about what that cosine of the angle means. In order to get a maximum amount of work, the force and the displacement should be either parallel or anti-parallel. So let's consider what happens if the force and the displacement are parallel. This means that both the force and the displacement are in the same direction. So here our angle would be 0 degrees. And if our force and our displacement are parallel, that gives us a decrease in the potential energy. However, if our force and our displacement are anti-parallel, means they're going in opposite directions. So here we'd have our force pointing in one direction, but our displacement would be in the exact opposite direction. And here the angle between our force and our displacement would be equal to 180 degrees. And when our force and displacement are anti-parallel, this will give us an increase in the potential energy. The last possibility is if our force and our displacement are perpendicular to each other. So here we would have our force pointing in one direction, and to be perpendicular, that means that our angle is 90 degrees. So here, if we were to look at the cosine of 90 degrees is equal to 0. And that's why if our force and displacement are perpendicular, the work is 0. And also there will be no change in the energy of the system. So let's apply this to some practice questions. So in this question, we need to determine for each of these charges what the change in potential energy will be as it moves as indicated in our diagram. Now remember, we can change the potential energy of a charge by doing work on that charge. Now in this question, we're given the electric field, we're given the charge, and we are given the distance. So the work will be force times distance. And remember, if we're dealing with electrostatics, the force, the electrostatic force is equal to the charge multiplied by the strength of the electric field, and then also multiplied by the distance. The orientation between our direction of motion and our force will tell us if we are increasing or decreasing in potential energy. Now in part A, we have a charge of 3 coulombs. That would be a positive 3 coulombs. And remember, if I have a positive charge, the electric field points in the same direction as the force. So here our electric force would be pointing to the left. And what we'll notice is the force and the displacement are in opposite directions, so we would see an increase in the potential energy. But by how much? Let's calculate that. So we'd say the work here, which would be our change in energy, would be equal to our charge, which would be 3 coulombs, multiplied by the field, 2 newtons per coulomb, multiplied by our distance of 0.05 meters. This would give us a change in energy of 0.3 joules. So we have an increase in our potential energy of 0.3 joules. Now notice that if we were dealing with a negative charge, if this was a negative 3 coulombs, if it was negative, our force would be pointing to the right. So we would have a force parallel to the direction of motion, and that would give us a decrease in the potential energy. Now let's look at part B. Here we have the same electric field, 2 newtons per coulomb. We have the same charge, but notice our distance, this 0.1 meters, is twice the distance as we saw in part A. So qualitatively, if we have double the distance, we would expect to see double the increase in potential energy. And we can also calculate this out. We would have 3 coulombs. We have 2 newtons per coulomb. We'd have 0.1 meters. And this would also give us 0.6 joules as our increase in potential energy. Finally, let's look at part C. In part C, we have twice the electric field as we saw in part A. So we would expect to see double the increase in potential energy as we saw in part A. Now, if we consider the force, again, we have a positive charge, so our force would also be pointing to the left. That would be our electrostatic force. Our force and our direction of motion are anti-parallel, so we would see that increase in potential energy. And the increase in potential energy would be equal to the charge of 3 coulombs multiplied by our field, 4 newtons per coulomb, multiplied by our displacement of 0.05 meters, which also would give us 0.6 joules. So now you should feel more comfortable calculating the change in potential energy as we move a charge through an electric field.